Hey everybody, Mr. Templin here. I am talking about this balloon problem to make sure that we're feeling good about the electrostatic force. Now, in the electrostatic force, we are talking about the force that two charges can repel each other or attract each other with. Those two charges get multiplied together up top, and we use the electrostatic constant, 9 times 10 to the 9th, Newton meter squared over Coulomb squared. And then we divide that by the distance between those two squared. Because this electrostatic force, as two charges get further and further and further and further apart, the electrostatic force gets weaker and weaker and weaker and weaker. Never quite to zero. There's always some little bitty force that two charges are going to attract each other or repel each other with, even as they're really far apart. So, let's take a look at these balloons, which are pretty far apart, 0.6 meters, and we'll see how much force that is. Because that's what we're asked to find here, the size and direction on balloon 2 in this situation. So the direction I can actually figure out first by thinking about, it's going to be pushed to the right by balloon 1, because that's a negative charge and that's a negative charge. So the two of these are going to repel each other a whole lot. And that force is going to be to the right. So whatever my answer is going to be is to the right. As far as the number, that's where the electrostatic force comes in. Also called the electric force, also called Coulomb's law. It's got a lot of different names, like pants and trousers. K, Q1, Q2 over D squared. So K we know. 9 times 10 to the 9th, Newton meters squared over Coulomb squared. Multiply by the absolute value of negative 60, that's balloon 1, times 10 to the negative 9th coulombs. Remembering that this had nano in it, and nano means 10 to the negative 9th. We're often going to see that for stationary charges, that they have really small amounts of coulombs. So it's really difficult to get one charge to stay still. This one over here is negative 80 times 10 to the negative 9th coulombs. And then divided by 0.60 meters squared. Well, if you're keeping track of your units, the meter squared cancels with the meter squared, and the coulomb squared cancels with the 2 coulombs. And if I put this into my calculator, I end up with 1.2 times 10 to the negative 4th newtons. And we already know that the direction is to the right. That's why this has an absolute value, because whatever you'll just get a positive number for the force, and then just look at the problem and think about whether the charges are going to repel or attract. And in this situation, they'll repel, which means balloon 2 gets forced to the right. Now, this second balloon gets brought into the party. Balloon 1 and 2 are still there. Those are the same two balloons that are up in that situation. But now balloon 3 is brought here, and it's brought a lot closer. Even without doing any math, because it's the same charge as balloon 1, I actually know that this force, that the force of 3 on 2 is going to be a lot bigger than the force of 1 on 2, that we already found out how big that is. We already know that's 1.2 times 10 to the negative 4th newtons. So this force, just to make sure I'm getting an answer that makes sense, is going to be bigger because this balloon is closer. And as we saw with the electric force, when you're closer, the force is stronger. So let's do this one. To find the net force, which is the sum of the forces, I need to find all the forces acting on this balloon. So first, I'm going to find out what the force is between balloon 2 and balloon 3. And keeping track of my nanos, 9 times 10 to the 9th times the absolute value of negative 80 times 10 to the negative 9th coulombs times negative 60 times 10 to the negative 9th coulombs, all over 0.30 meters squared. That tells me that the electric force is 4.8 times 10 to the negative 4th newtons, and in this case it's to the left. That totally makes sense because compared to the initial situation, I put this balloon twice as close. I halved the distance. And as you half the distance on one side, I'm changing one side of the equation, so I have to change the other. And I do that by 1 over 1/2 squared. Little algebra, 1 over 1/2 squared is 1 over 1/4 is 4. So this electrostatic force is going to be 4 times as strong as it was previously, and that's what I see. So this force right here is 4.8 times 10 to the negative 4th newtons, and this is 1.2 times 10 to the negative 4th newtons. When I sum them together, I need to say that one direction is positive and one direction is negative, and I'll call left negative. So the sum of the forces in the x direction says I've got negative 4.8 times 10 to the negative 4th newtons plus 1.2 times 10 to the negative 4th newtons. That's a right force, that's a left force. And it gives us a net force of 3.6 times 10 to the negative 4th newtons to the left. Note that when you add these together, you get a negative number, but negative means left. And so my overall force is going to be to the left, which makes sense with my picture that I drew. That I have more force to the left here than I have to the right here, so I'm going to get an imbalanced force to the left, and that is my answer. Make sure that you are good to go with problems just like this for your test.